Hello, I am Justin Huey, and today I'm doing problem 2.5 from the textbook, in which we'll find the electric field at a point P due to a ring of charge laying on the xy plane. Point P is at a distance z in the z-axis. So to begin with, let's write down our electric field equation. Our electric field is equal to 1 over 4 pi epsilon naught charge enclosed over the magnitude of script r squared in the script r hat direction. So to begin with, what is our script r vector? Our script r vector is equal to our source vector from our source point subtracted, no, my apologies, I'm sorry, it's the field point. Regular r is our field point vector, r prime is our source point. Sorry about that. So continuing on, our field point vector is equal to z in the z hat direction, while our source point vector is equal to big R in the s hat direction, the radial direction. All right, so now we could calculate our script r vector, which is going to be equal to z hat minus big R s hat. So let's draw our script r now. So script r will be going from the ring to the point P, going this direction, and there you go. There is our script r vector. So now let's draw our electric field. So we'll say that originating from right here, we'll call this one of our DQs, one of our differential charge elements. From here, since we already have the r script vector here, we could extend it out and draw our electric field. We're going to call that electric field 1. Now here at E1, what we could do is we could break this into components, as so, going these respective ways. So this bottom line here, what we're going to call it is we're going to call it E1 perpendicular to Z. And the other one is only in the Z-axis, so we're just going to call this our E1Z component. Now, if you'll see, if we come to the other side of the ring, and we'll call this element DQ2, and we do the same thing, we'll draw out our electric field. And we're going to call this one E2. We will break this into components, as so. And now this bottom one is going to be E2 perpendicular to Z, and then we have E2Z on this side. Now what you'll come to notice is that E1 perpendicular to Z and E2 perpendicular to Z, perpendicular to the Z-axis to be more specific, is that they are equal in magnitude, but they are opposite in direction, so they will cancel each other out. And you'll notice that due to the circular symmetry, any point here on the ring is going to have an opposite point. All the radial components, all the s hat components, are going to cancel, leaving us only with a net E field in the Z direction, the positive Z direction to be more specific. Now, how do we account for this? So we call this angle right here theta, and you'll notice due to symmetries and due to being projected off the same direction, these angles are equal. And we want the cosine component of this angle because we're looking for the adjacent side. Adjacent here is E parallel Z, adjacent here is Z. So using this angle, we could define what our cosine of theta would be. Our cosine of theta is equal to adjacent, which is Z, over script r, the hypotenuse, the magnitude of script r, sorry. And over here, let's calculate the magnitude of script r. So the magnitude of script r is equal to the square root Z squared plus big R squared. So now we could start substituting into our electric field equation to get closer to our answer. So right now, here's what we have. We have E is equal to 1 over 4 pi epsilon naught charge enclosed times script r, the magnitude of script r squared divided by that, times our cosine of theta. And since we're incorporating that cosine theta, we could say that this is only in the z hat direction. Okay, so now let's substitute in our cosine theta. So E is equal to 1 over 4 pi epsilon naught times our charge enclosed over script r cubed now times z in the z hat direction. now we have to account for our charge enclosed. So our charged enclosed is going to be equal to the integral of dq. And we know that dq is equal to lambda dl because it's a uniform charge distribution. So we can say that q enclosed is equal to the integral of lambda dl. Now what is our dl? What dl are we integrating over? We're integrating over the circumference of the ring. So that's just a substitution we can make. So q enclosed will be equal to lambda times 2 pi big R, the radius. Now that we have that piece, we could further make substitutions. Our electric field vector is equal to 1 over 4 pi epsilon naught times q enclosed, which we found to be lambda of 2 pi r over script r cubed times z in the z hat direction. From here, it's just a matter of substitutions. We'll substitute in what the magnitude of script r is equal to. Lambda 2 pi r over z squared plus r squared, 2 to the 3 halves, the z hat times z in the z hat direction. And this is our final answer for finding what the electric field is at point P. Thank you for watching.